Hello and welcome to this month's webinar from the IEA Clean Coal Centre. My name is Deborah Adams and I'm Communications Manager here. We do a webinar each month which is based on our technical reports which are available from our website www.iea-coal.org. Residents of member countries and employees of sponsoring organisations can download our reports at no charge after one-off registration. Please visit our website for details. Today's webinar is presented by Dr. Nigel Dong, who is an author and analyst here at the IEA Clean Coal Centre. His topic today is on pre-drying coal, the technologies and economics, and it's based on his report which has just been published today and is available on our website now. If you have any questions during the presentation, please use the Ask a Question box at the top of your screen. Add your email address as well so that Nigel can send you a fuller answer if we run out of time. Okay, Nigel, over to you.
Thank you, Deborah, for the introduction. Hello to everyone who participated in this webinar. This webinar presentation aims to give you an overview of the development status of modern drying technologies. I will also discuss the techno-economic information where available. What I'm going to present is based on my latest report and a previous report on low-rank coal and some updates from drying technology developers. Especially, I'd like to thank Professor Nenad Saranak from University of North Carolina at Charlotte and his colleagues at Great River Energy for updating me on DryFining, and Dr. Nikolaus Wambargen from RWE Power in Germany for updating me on WTA. WTA and DryFining are the two key technologies covered in my latest report. This chart shows you that lignite and sub-bituminous coals together account for more than half of the global proved recoverable reserves. At their current production levels, they could provide reliable supply for more than 200 years, while bituminous coal can last for a much shorter period of time. In some countries or regions, such as Germany, Greece, Thailand, and Australia's state of Victoria, low-rank coals represent the only available indigenous energy resource in large quantity. Therefore, these low-rank coals are strategically important energy resources. With hard coal reserves being gradually depleted, global coal use is shifting to low ranks. Notably, power utilities in China and India are importing coals of lower heating values in a range of 3,800 to 4,200 kcal per kilogram from Indonesia, which are priced much cheaper than hard coal products. However, the biggest problem with ongoing use of low-rank coals is their high moisture content. As shown in the chart on the left here, it is common for these coals to have 30% plus moisture. The moisture content of some German and Victorian coals can be as high as 60%. The chart on the right shows that high coal moisture content can considerably reduce the thermal efficiency of the power plant that fire these coals. This is because a significant portion of the energy contained in the coal is used to evaporate the moisture out of the coal, and is thus not used to raise steam and contribute to electricity production. Since the energy carried away in the evaporated moisture is not recovered, the net thermal efficiencies of the power plant decrease considerably, and more CO2 is emitted on an equivalent energy output basis. Pre-drying low-rank coals before entering the combustion furnace of plant boiler is the most effective way to overcome these issues. However, deep drying of high moisture coal is not an easy task. As shown in this schematic, moisture is present in various forms in coal particles. From particle surface to interior, free moisture removal becomes more difficult and consumes more energy. Inherent moisture is even harder to remove because it is hydrogen bonded to coal mass. so need chemical treatment or more extensive heating to break down the hydrogen bonding to remove the inherent moisture from the coal. Consequently, deep drying in an energy-efficient way is a key challenge to develop effective drying methods. There are more than 70 different coal drying technologies that have been patented, but the number of drying technology that goes from technology concept to actual development is much smaller. Drying technologies can be classified based on their salient features. On this slide, drying technology are broadly grouped into 4 blocks. In the top block, rotary dryers and flash mill drying are mature technologies and are widely used in briquetting plants and power plants, but they are energy intensive and have the risk of fire and explosion because hot air is used. The 4th block down in the bottom represents innovative drying methods, which are in the early stage of development. Drying technologies in these 2 blocks are not discussed in my reports. The technologies in the 2nd block are based on the evaporative drying principle, while the 3rd block involves mechanical forces for drying. These represent the mainstream drying technology development. I will talk about fluidized bed drying in a bit more detail because they are more advanced in development status, and there are some publicly available information on their technoeconomics. For the other drying technologies, I will just briefly introduce their features with an example. Let's first look at 2 drying technologies that are based on fluidized bed system. Drying coal in fluidized bed is popular because it offers high heat and mass transfer rates. RWE in Germany has developed a steam fluidized bed dryer with internal with heat utilization, known as WTA in German abbreviation. WTA has a closed cycle and an open cycle variant, depending on the source of heating steam. This flow chart shows the open cycle variant. The coal bed is fluidized by the recycled steam from coal moisture, and the drying heat is mainly provided by the steam bled from the low-pressure turbine of the associated power plant through a heat exchanger immersed in the fluidized bed. The size and operational performance of the dryer can be optimized by taking into account 3 key parameters, including coal particle size and size distribution, fluidized bed pressure, and heating steam pressure. WTA has been successfully demonstrated in a commercial prototype dryer at Niederrosten Unit K in Germany, which uses the open cycle design. The capacity of the prototype dryer is 110 tons per hour of dried lignite, and RWE said commercial dryers would be no larger than this capacity. The results show that the moisture content can be reduced from about 50% to 12%. The dry lignite can replace up to 30% of the fuel input on an energy basis without the need to significantly modify the boiler furnace. This leads to about 1 percentage point gain in thermal efficiency and 2.5% reduction in CO2 emissions. There's no complete data publicly available on investment and O&M costs of this WTA prototype dryer, but in 2009, RWE reported 50 million euros budget for this prototype project at Niederrosten. An RWE study shows that in a BOA plus lignite power plant, where all the fuel feed is dried lignite, the additional capital expenditures can be almost fully offset by savings resulting from firing dried lignite. This means the capex of the entire power plant will barely increase, but an efficiency gain of 4 to 5 percentage points can be realized. Some researchers in Greece studied the impact of pre-drying using WTA dryers on the generation cost of power plants. The reference power plant is a 590 megawatt supercritical power plant that fire a Greek lignite with 53% moisture content. Pre-drying, 25% of the fuel input and 100% of the fuel input were examined in the study respectively. As you can see from the stacked column chart here, the results shows that the installing and using WT dryers slightly increased the annualized capital expenditure and O&M cost, but reduced the annualized fuel cost. As a result, the overall generation cost barely changed compared with the reference plant. But if you take the CO2 emission cost into account, the overall generation cost of the dry lignite-fired power plant actually decreased. DryFining is a pre-drying technology based on a moving fluidized bed system, but the fluidizing medium is warm air, not steam. It is developed by Great River Energy in the USA. As shown in the flowchart here, the heat for drying comes from the low-grade heat in the flue gas and cooling water that would be wasted if not recovered to dry the incoming wet coal. As suggested by its name, DryFining can not only dry the coal but also beneficiate the coal. Beneficiation takes place in the first stage of the dryer, where mineral-rich materials can be gravitationally segregated and removed from the coal. In the second stage, the refined coal is dried in warm fluidizing air and then cooled in the third stage and discharged from the dryer. DryFining technology was successfully demonstrated at a commercial scale at Unit 2 of Coal Creek Station in late 2000s. Subsequently, the 2 units at the Coal Creek Station installed DryFining dryers and fully converted to dry lignite firing since 2009. The lignite moisture is reduced from 38% to 29%. Firing dried coal results in about 4% fuel savings, 4% gain in efficiency, and a significant reduction in air pollutant emissions. No complete economic information is publicly available. It is known that U.S. Department of Energy contributed $13 million in total to fully convert Unit 2 to dry lignite firing. Great River Energy funded the conversion of Unit 1 and disclosed that the investment cost was $240 per net kilowatt for the first commercial installation, and said this cost could be reduced to $80 to $120 per net kilowatt for future retrofit installations. The estimated O&M cost was $350,000 per year for one 125 short-term per year dryer. The benefit gained from the retributing dry firing dryers to Coal Creek Station seemed larger than the cost incurred. As shown in this chart, the net per megawatt hour savings is around $1 or $20 million annually, which results largely from fuel savings and reduced auxiliary power consumption. HRL in Australia developed a dried bronco-fired IGCC technology as an alternative power generation technology to conventional powerized coal-fired power generation technology. The key feature is that hot crude syngas is used to dry the incoming wet brown coal, so the feed to the gasifier is dried brown coal. The moisture vapor carried by the syngas is able to add to the power output from the gas turbine. A 10 megawatt demonstration plant has been developed at Morwell in 1996 with a reported high heating value efficiency of 40% without sulfur removal. A 600 megawatt commercial demonstration project was planned, and initially with support from funding's with support funding from both the Commonwealth and the state governments. But recently, the Commonwealth government withdrew the funding, so the project is now suspended. But some considerable progress has been made, so HRL continues to explore new funding opportunities to continue this project. Hydrothermal dewatering is based on the principle that removing the coal moisture in liquid form under moderately high temperature and pressure. Compared with evaporative drying, the latent heat of evaporation of moisture is avoided. Therefore, the drying efficiency is improved. Drying under those conditions also partially paralyzes the coal. Coal tar evolves during pyrolysis, seals some small pores, so that the moisture reabsorption problem is reduced. A major issue is that the removed water effluent contained organic and inorganic contaminants, so there's treatment before being discharged. No satisfactory treatment method have been developed so far. Sorry, it's the wrong slide. The example given here is the continuous hydrothermal dewatering process developed by the Australian company Oxygen. The key feature is the 1,000-meter-long autoclave in which coal is partially paralyzed under 10 megapascal and 300 degrees C. This technology has been proved at a 4-ton per hour pilot scale in Tasmania between 2004 and 2012. A 50-ton per hour pre-commercial demonstration project was planned to be built at the Morwell Power Station in Latrobe Valley in Victoria. Densification dry involves using attrition forces to destroy coal pores and expel water, followed by drying with warm air. The most known densification-based drying process is probably the coal dry, developed by Australian company ECT. This technology has been proved in the batch mode pilot plant with a 1,000-ton per year capacity. Tests in this plant show that coal moisture could be reduced from 35 to 65% to 12%. ECT is now looking to demonstrate and commercialize this technology in India and Victoria. Another drying method that uses mechanical force is mechanical thermal expression. The principle is to use high-pressure compression force and heat to expel the water out of the coal. This drying method is less energy-intensive compared to most thermal drying methods. But the key issue is similar to hydrothermal dewatering. The effluent from the process is contaminated by organic and inorganic materials, so it needs to be treated. And no satisfactory treatment so far has been developed. Also, almost all development have been based on the batch mode, but for commercial application, fully automated continuous operation is necessary. Aircraft in Australia have demonstrated a continuous process which used match steel conveyor belt. GTL Energy developed a patented and proprietary coal upgrading technology that is based on mechanical thermal expression. Tests have been made on coals from Indonesia, New Zealand, and North Dakota. Results show that coal moisture could be reduced from 40% to 14%. Its technology has been in commercial operation in Solid Energy's 100,000 ton per year Mataura drying facility in New Zealand. Microwave drying is a novel evaporative drying method. It makes use of the selective absorption of microwave energy by water to achieve effective removal of both surface and inherent moisture while keeping the main coal mass at a low temperature. This diagram shows the dry coal dryer developed by DBA Global in Australia. Wet coal is sent on the conveyor belt into the drying chamber, where the coal particles are subject to microwave energy and dried, and the dried product is moved out of the dryer on the conveyor belt. Both coking coal and Powder River Basin subbituminous coal have been tested. The American company Coaltech also developed a microwave drying technology, and a 15-ton per hour commercial scale drying facility had been built in Kentucky. My previous report had also discussed some coal upgrading technologies. I don't have the time to go through them today, so I just want to point out that coal drying is an important part of coal upgrading. As shown in this table, all the upgrading technologies incorporate some type of drying methods. The coal upgrading provides an important path to convert low-value, high-moisture coal to high-value products that can be safely and economically transported to capture remote market opportunities. I'd like to wrap up my presentation with a few remarks. There are plenty of technology options for drying coal, but few have reached commercial deployable status. A commercially deployable drying process needs to be technologically proven and efficient, scalable with acceptable size, capable of being integrated with other coal using facilities, and most importantly, its cost should be affordable. In addition, for commercial application, there needs to be markets available for the dried products. All these have to be demonstrated at a commercial scale so that customers and financiers can understand the risk, cost, and time to market. This is the key to the commercial success of any coal drying technologies. That's all I got to say today. Thanks for your listening, and I'm happy to take questions if there are any.
Thank you very much, Nigel, for a really interesting presentation. While we wait to see if any questions have come in, I'd just like to tell you that the next webinar takes place on the 8th of October, where Carl Nickel will be presenting on coal beneficiation for the direct injection carbon engine. Okay, let's see if there's some questions. Okay, the first question for you, Nigel, is this one. What's the main difference between evaporative drying and non-evaporative methods?
Thank you. Well, the main difference is that evaporative drying incurs higher energy penalty than non-evaporative method. This is because evaporation involves the latent heat of steam, which is approximately 2.4 megajoule per kilogram of steam. Since most evaporative drying processes involve no heat recovery, so the energy requirement, is higher, probably in a range of 3 to 4.5 megajoule per kilowatt of moisture removed. By contrary, the energy requirement for non-evaporative drying process is generally lower, typically between 1 and 2.5 megajoule per kilogram of moisture removed. In addition, there are differences in process system design. For example, for mechanical thermal expression, automation of the process from a batch mode to a continuous mode is a key challenge, while for most evaporative drying processes, continuous processing is generally not an issue. I think these are the main differences. Thank you.
We've had another question come in asking for a copy of the presentation, which reminds me to tell you that the PowerPoint will be uploaded onto the webinar page of our website later on today, and you can download a copy of the PowerPoint from there. Okay, there's another question for you, Nigel. Which technology do you recommend for drying of low-grade coal as a standalone plant?
Well, that's a difficult question to answer. I mean, you have to. It really depends on the purpose of that drying, process. So far, I don't think there's a clear market winner because each drying technology has its pros and cons. Particularly the economic efficiency is not widely available. So I don't know. But I can't tell which one is better than others, to be honest. Thank you.
There's another question come in. How do lignite drying processes reduce emissions of CO2?
I guess the question is in the context of power generation. Well, if you burn the wet lignite, a considerable portion of the energy contained in lignite is used to evaporate the moisture out of the coal in the boiler surface. So that part of energy is not used to raise steam and generate electricity. So therefore, to generate a certain amount of electricity, more lignite needs to be burned. So that's why the CO2 emission is higher compared to a hydrothermal power plant with the same electricity output. So that's why if you dry the lignite before burning it into the boiler furnace, you can reduce the CO2 emissions per unit useful energy output. I think that probably answers your question.
Yeah, I think so. Now, here's the last question at the moment. Is there any further development on steam-heated rotary tube dryers, such as the ZEMAG, Z-E-M-A-G? Is there any vapor or water recovery after this? What do you think about that, Nigel?
Yes, I mean, I read some papers that discuss the further development of the rotary dryers. Well, basically, I think it basically combines the rotary dryers with some air aeration methods to speed up increase the drying efficiencies. Regarding the specific question you raised, I'm not very sure. I have to go back to check it. I probably can get back to you by emails. I'm not sure at the moment. Thank you.
Also, if you'd like more detail than Nigel's been able to give today, don't forget that the report has been published, and if you register at our bookshop, you can download it today. There's one more question come in, which I think is similar to one you've already had, Nigel, about which drying technology do you see as a winner. But I think from your previous answers, it all depends on the coal and the circumstance. But I'll let you give a bit more information.
Yeah, I mean, it's probably fair to ask the question which technology has been further developed. So from that perspective, I think the WTA and the Great River Energy's DryFining has achieved a more advanced development, but that doesn't mean the other technologies have less advantage. You got to compare them and also to decide them according to the purpose of drying. So I think that's probably a better way to raise the question, I guess.
Thank you. Right, now I think this genuinely is the last one. Nigel, what determines the maximum moisture removal level for retrofitting pre-drying processes to existing lignite-fired power plants?
when retrofitting pre-drying process into an existing power plant, I think the key guideline is pre-drying should not affect the operation of the boiler and the steam parameters. Take DryFining as an example. Some cold moisture needs to be retained because moisture evaporates and adds volume to the flue gas, which increases the velocity through the superheater pendants, and so increase the heat transfer into the reheat system to achieve the desired reheat system temperature. So therefore, the moisture removal is limited by the need to maintain the desired reheat steam temperature. It is also determined by the amount of heat available for drying without severely affecting the thermal cycle of the power plant. Otherwise, the net electricity output will be reduced and the efficiency gain may be compromised. Thank you.
Okay, that's all the questions answered. Thank you very much, Nigel. So just remind listeners that the PowerPoint will be available to download from our webinar page later on today, and the report is also available from the website. And if you've got any further questions, do email Nigel at the address given on this last slide. And don't forget to tune in on the 8th of October for Carl's presentation on the direct injection carbon engine. Thank you very much for listening. Goodbye.